There's two different things. There's a store of energy and there's a transfer of energy. We're going to look at both. So energy stores, get this up again. So for energy stores, there's 8 different energy stores you need to know. Energy transfers, there's 4 different energy transfers that you need to know. Most people are saying C. C is correct. C is one of them. Can you guys tell me any of the other ones? So we'll write this down. We got chemical, other ones. Kinetic, yes. So that's anything that moves has kinetic energy. Gravitational potential, nice. Elastic, thermal, very good. Electromagnetic is not a type of energy store. No, it's not. So we've got 3 more. What do we have? Let me see comments, see if there's any others that I've missed out. We've got magnetic, that's another one. And we've got 2 more. Electrostatic, yes. And last one, yes. Well done, guys. Last one is nuclear. Okay, so all 8, those are the 8 energy stores that you need to know. I've got I posted a video on this, I think like last month, going through each one and what type of objects have each one. So it'll be useful to look at that if you want. It's every single energy store that you need to know. Let's go back to our question then. So we talked about chemical was a type, and we've just written all the other 7. Energy can be transferred by all of the following methods. So now we're talking about energy transfers. There are 4 energy transfers that you need to know. Do you guys know what they are? We'll list them out now. So comment your answer if you think you know an energy transfer. Energy transfer is basically when energy goes from one store to another. So yes, by radiation, thanks Grace. So what does that mean? That means when it travels as a wave, so like light or sound. Electrically, yes, so light and sound comes under radiation. Electrically, that's when it travels through an electrical circuit. So any appliance that has an electrical circuit in it will have electrical energy transfers. Yes, those last 2, thank you, well done guys. Mechanically, we can call that mechanical work as well, and by heating, well done. Okay, so we've got our energy transfers, we've got all our energy stores. So these questions that we look at, it's going to be to do with most of these. So energy can be transferred by all of the following methods except, so which one of these were not one of the ones on the list? So just quickly vote what you think the answer is and tap on the screen a few times. Yep, well done. Most of you are getting the answer. That doesn't make sense. Stillness is not even anything you do in physics. It's not part of any topic. So heating, we mentioned by radiation, and mechanically we all mentioned stillness is not one. Which energy store does a stretched or compressed spring have out of the following? Why don't you guys vote and let me know. This one's a quick one as well. You can tell by the name. It's a spring, so you can tell by the name. The answer is, yep, D again. Elastic potential. Whenever you have a stretched object or a compressed object, this is one that people forget. It's also compressed. If you have a spring and you squash it and you let go, all of that elastic potential energy that's been stored gets transferred into kinetic energy and it basically moves, doesn't it? So it's not just stretching an object, it's compressing as well. The answer is elastic potential energy. Well done, guys. Okay, let's look at a quick exam question here. So we've got a multiple choice question. We've got a pulley and we've got a lift. So the lift is being pulled up by an electric motor and there's a counterweight here. This is just a weight that goes downwards as the lift goes upwards. Okay, so as the lift moves up, how far does the counterweight move down? So basically, if the lift moved up 10 meters, how many meters would the counterweight drop down? It's very straightforward. It's a bit of common sense, hopefully. It's going to be the same. If this goes up 10 meters, the string's not disappearing. The string is exactly the same length. So if the lift goes up 10 meters, then the counterweight is going to go down 10 meters because you have the same length of string in the middle. So the answer is the same distance as the lift. And that's the answer for that one. So just checking that with the mark scheme. Yep, same distance as the lift, just to confirm that. On to the next question. What happens to the gravitational potential energy of the counterweight as it moves down? Gravitational potential energy. Can anyone tell me the equation for that? Gravitational potential energy. We'll write it down here. We've got a few energies that we need to go through. Gravitational potential energy. In your equation sheets is EP actually. Mass times gravitational field strength times one more thing, mgh. Yep. So mass times gravitational field strength. Can anyone tell me what gravitational field strength on Earth is? Yes, well done. 9.8. So on Earth, this is 9.8 newtons per kilogram. The units for these, joules. Mass is measured in kilograms. Gravitational field strength is measured in newtons per kilogram and height is measured in meters. I'll upload this, all these notes, guys, at the end. So in the next few days, I'll upload the notes. So don't worry about writing everything down. So what happens to the gravitational potential energy as it moves down? So what's happening here? The equation that we just wrote was mgh. What's happening? The height is decreasing. So that means that the gravitational potential energy is also going to decrease. So gravitational potential energy, as it moves down, it decreases. The answer's decreasing. Where am I going to post this? I'm going to post this on YouTube, guys. Flash Revision Lab on YouTube. I'll post all the questions, all the notes as well as the video. Okay, next question is a calculation question. Calculate the gravitational potential energy when the mass is 1,300 kilograms. Gravitational field strength is 9.8, so they've given that to us. We want to work out when it moves up 4 meters. So it's just a case of subbing in the numbers. So E is equal to 1,300, that's our M, times by 9.8, that's our gravitational field strength, times by 4 meters. Put that all into your calculator and you should get the answer. So if you've got a calculator, try that now. I'm just gonna put a quick poll up while you guys do that. If you're doing it, just let me know if that makes sense. My explanation makes sense. I'll to know what example people are. Just answer. I've just put a poll up. Let me know. So answer yes. Well done, those of you who've written it. 5,000. Around 50,960 joules. That's the answer. So let's look at that. On the mark scheme, it decreases. We said that. And then we got the answer here. It's 50,960. Hope that makes sense. Let's move on to the next question. So same thing again. We still got this pulley. This time, we've got the equation for elastic potential energy. So let's write that down in our notes. Elastic potential energy, so that's E is equal to half times K, which is the spring constant. The spring constant basically tells you how stiff a material is, how stretchy it is, times by extension. That's how much you stretch it by. It's extension squared. So if we get spring constant, which is measured in Newton per meters, extension is measured in meters, and energy is measured in joules. So we can try that here now. Got our extension here, got a spring constant here. So we've got everything that we need. So someone try that if you've got a calculator. 0.5 times by 880,000 times by extension squared. Remember to square just the extension, not the whole thing. Don't put everything into your calculator and then just do answer squared. That's going to be wrong. So start off with the 0.015 squared and then times the other two numbers. Let me know if anyone gets the answers. Doing it as well. Anyone got the answer yet? Yep, 99. Well done. So 99 joules is what you should get. Do that. Next question. A lift system using a counterweight is more efficient than a lift system that does not use a counterweight. How does it having a more efficient system affect the energy transferred by the motor? So look at what we've got here. We've got a motor that's pulling the lift up. Okay, imagine it's quite a heavy lift. So the motor needs to do quite a lot of work. But the counterweight is helping the motor do work because it's pulling itself down. So it's pulling the lift up. So that means the motor has less work to do. So that means the motor has less energy to transfer. So less energy is transferred, making it more efficient. So remember, it's increasing efficiency. It's more efficient. So that means if it's more efficient, it needs to release less, it needs to use less energy. So less energy needs to be transferred. So the answer is less energy transferred. Let's just double check our answers. Yes, we got 99 joules there and less energy is transferred. So well done. Next question. What is the energy store called that is associated with the height of an object? So we've already done this. So let me know what you guys think. This should be a quick one, hopefully. The height of an object. There's only one in this list that has height in it. So the answer would be B. Yeah, B is the answer. That's the only one that's got height in it. The equation is mgh, mass times gravitational field strength, times by height. When an object speeds up, its what energy store increases. So what energy store is to do with speed? There's one that's to do with movement. What's the answer? Yes, we're quick to answer this one. The answer is kinetic energy. Kinetic energy is to do with movement. So the more an object moves, the more kinetic energy it has. Does anyone know what the equation for kinetic energy is? Kinetic energy, it's got to have a speed. It's got to have speed in it. Half times mass times velocity. Yep, let's write that down. So EK is equal to half times mass times speed or velocity squared. Again, Energy is measured in joules, mass is measured in kilograms, speed is measured in meters per second. The answer is kinetic. The specific heat capacity of a substance is the energy required to do what? So this is something we haven't written an equation for yet. Specific heat capacity, what's the answer? Let me know. A, B, C, or D. May you show us formulas? Yep, I'm writing all the formulas down here. So we've got kinetic energy formula here. We've got gravitational potential energy. We've got elastic potential. We're going to write the specific heat capacity one down as well. Can anyone tell me what the specific heat capacity equation is? Most people are saying B for this. Raise the temperature of 1 kilogram of substance by 1 degree Celsius. Yes, that's the definition of it, of specific heat capacity. The equation for specific heat capacity is, so this is how it will come up on the equation sheets. So change thermal energy equal to mass times specific heat capacity times temperature change. Yes, well done, those of you who are saying that. So change in thermal energy is measured in joules, mass is measured in kilograms, temperature change is measured in degrees Celsius, specific heat capacity, this has got a weird one, joules per kilogram per degrees C. Like so. So we'll probably be using that at some point in this session. Next question. What is the formula for calculating change in thermal energy? So we just wrote this. The answer is this one. So that's the shorthand form. Energy. So change in thermal energy. Mass. We use the C for specific heat capacity and this delta theta symbol for change in temperature. All right, on to an exam question. So here we've got a child on a trampoline. There's two different positions. So this is position A, where the child is basically falling from that position to position B. They've landed on the trampoline in position B and they've basically stretched it a bit. So they're kind of still at that point. The question asks, describe the changes to the stores of energy. So remember the 8 different stores that we looked at of the child, spring and surrounding. So let's look at the child first of all. The child starts off at this level, then the child ends up at this level. So what energy is being transferred here? What would you say? What's changing here? It's basically their height, isn't it? They're going down. So what type of energy is being changed here? There's only one type of energy that's to do with height. So it would be gravitational potential. Yes, thank you. So what's happening is the gravitational potential, I'm just going to write GPE for short, is decreasing because they're getting lower down, isn't it? As they're falling, as the child's falling, their height is getting lower down. So what's increasing then when they're going lower down? So gravitational potential is decreasing. There's something that's increasing. Yes, thank you. Kinetic energy is increasing. Why? Because remember, kinetic energy is all to do with movement. If this child is moving down, then they're gaining kinetic energy. They're getting faster, aren't they, as they're falling? So their speed is increasing. The equation for kinetic energy is half mv squared. So if their speed is increasing, their kinetic energy is increasing. So kinetic energy, I'm going to put kinetic E, is increasing. But that's not all, because they're falling down, but then at that final position B, there's one more thing that they're doing. They've stopped, isn't it? At this position here, they're no longer moving downwards. So at that point, what happens to kinetic energy? Increases up to that point, and then all of a sudden it goes to 0 because they stop moving. For that split second where they've landed on the trampoline, the kinetic energy goes to 0. So we can say, and goes to 0. Okay, so that's the child. Now let's think about these springs. So trampoline has springs on the side. So at position A, what do they have? Position B, what type of energy is increasing or decreasing? Yes, thank you. Elastic potential energy is increasing because it's asking about changes. You can't just say elastic potential energy. You have to say whether it's increasing or decreasing. So good, elastic potential energy increasing. Then we've got the surroundings. What do you guys think about that? That's for the final mark. What's happening to the surroundings as these springs stretch? Surroundings, yes. Usually for surroundings, it is thermal energy. You can't say sound because sound is not one of our thermal energy stores. The question is specifically saying thermal energy stores. Sound is not one of our energy stores. Sound is basically one of our energy transfers. It comes under radiation. So you can't say sound as your energy store. The answer is thermal energy. Yes, the kinetic energy, it's being converted to thermal energy. So what's happening is thermal energy increases. Okay, hope that made sense. Let me know, guys, did that make sense? I'm just going to put a quick poll. Just vote now. Did that make sense? All my explanations. So position A, so for first one, GPE is decreasing because they're going from a high level to a low level, and then their kinetic energy initially increases because they're falling down, and then it goes to 0 because they've basically stopped for a split second, haven't they? When they reach the bottom of this trampoline, they've stopped. And then for the springs, the elastic potential energy increases. Elastic potential energy is all to do with things being stretched or compressed. So when this child lands on the trampoline, the springs are getting stretched. So that increases. And then for the surroundings, the thermal energy increases because it's basically releasing heat to the surrounding air. Okay? Thanks for voting, guys. So it looks like most of you, yeah, nearly all of you understood. Let's just compare to the mark scheme. So we said this, GPE decreases, kinetic energy increases, and see, that's bold. On a mark scheme, if it's bold, it means you have to say both to get this mark. Kinetic energy increases and then decreases to 0. Next one, springs, elastic potential increases. We said that, we said this, thermal energy increases. So we got all 4 marks. So that's good. Well done, guys. Next, we have some sort of calculation. 5-mark calculation. This is a big calculation. So when a child is at position A, the spring is stretched by this much. Elastic potential energy of each spring is this. When the child is at position B, the elastic potential increases to this. Calculate the extension of each spring when they're at position B. Right, let's get, if you've got a calculator, guys, it'll be useful. There's 2 parts to the calculation. The first is at position A. Let's look at our information in position A. Position A, we've got 0.056 meters and 4.9 joules. We need to use our elastic potential energy equation. There it is, this one. We need to use this equation. Half KEX squared, KE squared, KEX squared, sorry, KE squared. Half KE squared. So what you can do, you need to work out K, first of all. You want to work out the spring constant, and then that spring constant, because we've got the extension and energy, we can work out spring constant first, and that spring constant is then going to help us work out the elastic potential energy. It's going to help us calculate the extension at position B. So we need to rearrange this equation. So elastic potential energy divided by, so we're going to move this to the other side of the equation, and we're going to move this to the other side of the equation. So elastic potential energy divided by half times extension squared. Elastic potential energy we've got as 4.9 here. 4.9 divided by half times our extension, which was 0.056. But remember to square that. 0.056 squared. That's what you need to put in your calculator. So if you put that into your calculator, anyone done that yet? So if you put that into a calculator, remember to square this separately, yeah? Don't forget to square that. Yep, 3125 you should get. 3125. So that's the spring constant. So once you've got your 3125, you use the same equation at position B. So let's look at the information we have for position B. When the child is at position B, they have an elastic potential energy of 8.1. So we're using the same equation again. Elastic potential energy equals to half times spring constant times extension squared. This time, we want to work out the extension. So we want to make extension the subject of our formula. So what we're going to do is we're going to move the half and the K across. So extension squared is equal to elastic potential energy divided by half times spring constant. When you do that, you also need to remember to square root it at the end as well. I'm going to move this square to the other side of the equation and square root it. So let's put all our numbers in. What do we have? We've got elastic potential energy as 8.1, don't we? So we're going to do 8.1 divided by half times spring constant, which we just calculated, as 3.125. And then don't forget to square root that all at the end. And then when you square root all of that, yes, someone's got it. Well done. Final answer should be 0.072 meters. Okay, so if you're trying it out, then try put it in the calculator. See if you can get that. Let me explain that again. So we've got our first step, which is to find out the spring constant. We rearrange the equation to make spring constant the subject, and then we sub in all our numbers. Remember to square the 0.056. That gives us 3,125 Newton per meter. Then you can put it into the same equation again at position B, and that will give you 0.072 meters. All right. Sorry guys, I got a bit of a cough right now, so I find it get hard to talk. So let's just check the mark scheme. We've got 3, 1, 2, 5. That was fine. And we rearranged this equation and then we ended up with 0.072. All right, let's look at the next question. I want you guys to answer this. Vote what you think the answer is and tap on the screen a few times. I'm just going to get a quick drink of water. Yeah, so most of you got watts. Watts are the units for power. Does anyone know the equation for power? Power is the rate of energy transfer or rate of work done. Energy over time. Yeah, power is equal to energy divided by time. Energy is measured in joules. Time is measured in seconds. Power is measured in watts. So the answer for this is watts. How is efficiency calculated? Out of these ones, what do you guys think the equation for efficiency is? Vote your answer and tap on the screen a few times. Equation for efficiency. A, useful energy output over total energy input. Yes, times 100. You got to times it by 100 at the end. That is the equation for efficiency. That tells you how much useful energy an appliance is doing compared to how much it's wasting and dissipating. What does the conservation of energy principle state? So what's the main thing that you can say about energy out of these ones? What's basically true? Energy can be created or destroyed. Energy is only transferred from one form to another. Energy can vanish into nothing. Energy can only be converted into heat. Most of you are putting B. Yeah, B. Energy can't be created or destroyed. It can only be transferred from one form to another. Done? Answer is B for that one. Which energy transfer method is primarily used by a phone in operation? So if you're using a phone, which of these transfers are you going to use? These are the 4 different transfers you need to know. Mechanically, by heating, radiation, or electrical. What do you guys think the answer for that one is? So remember what I said. So a phone has got a circuit in it. So we've got people saying radiation, people saying electrical. It's not mechanical. Mechanical is when you use a force to transfer energy. In a phone, it's not really using a force. Heating is when heat is being transferred. Heat does get transferred in a phone, but that's not useful. The heat is not there to warm you up, basically. The answer, if anything has an electrical circuit within it, the answer is electrical energy. The way it works is energy is transferred electrically through the circuit to whatever it needs, to the speakers to make sound, or to the screen to produce light, or in the battery as chemical energy. Car braking converts kinetic energy into what? So a car has kinetic energy. Why? Because it moves. When it brakes, that kinetic energy gets turned into what type of energy? Definitely not nuclear energy. People are voting for D. Elastic potential wouldn't really make sense. Gravitational potential is all to do with height. If we assume the car's flat, the gravitational potential energy is not going to change either. The answer is thermal energy. All right, next question. This is part D of some sort of question. It doesn't matter what the previous parts are. The kinetic energy of the boat. The question was about a boat. So let's say a boat has a kinetic energy of this. We've got the mass, calculate the speed. There's only one equation that we have to use here, that we can use if we base it on everything that we've got, or the equations that we've got. It's going to have to be the kinetic energy equation, half mv squared. What do we need to remember to do before we sub the values into the equation? Can anyone tell me? Half mv squared. So yeah, you got to rearrange the equation and the units. Yes, the units is the most important thing right here, because look at this. This is 81 kilojoules. Here, this is measured in joules. So we need to convert everything into joules. So how do you convert kilojoules into joules? You do 81 times 1,000. If you want to do kilojoules, joules, you times by 1,000. If you want to go joules back to kilojoules, you can divide by 1,000. So that gives you 81,000 joules. That's the first step. Now we get our equation. We want to work out speed. So we need to rearrange the equation to make speed the subject. So what we're going to do, just like we did for the elastic potential energy, we're going to move 2 of the things across. The half and the m, we're going to move to the other side of the equation. So we end up with v squared is equal to kinetic energy divided by half times mass. And then let's move the square across as well. That's going to give us a square root. Now we can sub in all the values in. So our kinetic energy is 81,000. Divide that by half times the mass that we've got here, 8,000. Anyone got the answer? Yes, looks like people are getting it. Well done, guys. When you put that into your equation, it should be 4.5 meters per second. Let's just check that with our mark scheme. Get a mark for the conversion. Then we subbed everything in, we rearranged it. Remember to square root it. Loads of people forget to square root it at the end. And we've got 4.5. So 1, 2, 3, 4 marks. Fine. Okay, part E of that question. So we still got the boat. It's passing over a wave, so it's going to move up higher. So that means if it's moving up higher, it's going to affect the gravitational potential energy. Because remember, gravitational potential energy depends on the height of an object. The higher it moves, the more it gets. Equation for gravitational potential energy, which we've already written in our notes, is mgh. We've got our energy, we've got our mass, we've got our gravitational field strength. We want to work out height, so we want to make height the subject of this formula. Everything's also in the correct units. There's no conversions here. If you compare this to the equation we have in our notes, there's no conversions needed. Everything is in the correct units. Joules, kilograms, newtons per kilograms as well. So we can just sub everything in after rearranging the equation. H is equal to gravitational potential energy over mass times gravitational field strength. So that is 19,600. If you get the answer, let me know, guys. 19,600 over 8,000 times by 9.8. No square root needed this time. Let's see what everyone's getting. 0.25. Someone got 21.1. Most people are getting 0.25. Yeah, the answer should be 0.25. Just make sure you do this separately to the 19,600. Maybe put them in brackets if you didn't get that answer. Maybe that's the problem. Yeah, that's the common mistake people forget. Because this is at the bottom, just put it in brackets. If your calculator doesn't have the function where it can do numbers as a fraction, then make sure you put the things at the bottom in brackets. Otherwise, it's going to do 19,600 divided by 8,000 first, and then it's going to times the answer by 9.8. That's not what you want. But yeah, your final answer should be, yeah, exactly. Your final answer should be 0.25. Well done. Next one, the rate of doing work or the rate of energy transfer is defined as, so we've already wrote this in our notes. Let me know what you think the answer is, and then tap on the screen a few times. The rate of energy transfer or the rate of doing work, A, B, C, or D. So we've got some people saying that we've got B, and we got C, and we've got someone saying A as well. No one saying D because it's not D. Any other votes? What do you guys think? Rate of energy transfer. We did write this in the notes earlier. Someone else with B. Yeah, most people are saying B. B is the correct answer. Power. That's the definition of power. The rate of energy transfer or the rate of work done. Which factor does not affect gravitational potential energy of an object? So out of all of these, what do you think the answer is? You just need to remember the equation and see what's not in the equation. If something's not in the equation, then it doesn't affect it. So we've got people saying C. Yeah, because it's to do with the equation. Gravitational potential energy, equation for that is mgh. That means only m, g, and h affects it. So mass, height, and gravitational potential energy all affect it. Shape does not affect the gravitational field, gravitational potential energy. So the answer is C. If a machine has an efficiency of 80%, what happens to the remaining 20% of energy? So it's all to do with efficiency. What do you guys think the answer is here? A, B, C, or D? Yeah, if it's 80% efficient, that means 80% of the energy is transferred usefully, and the remaining 20% is waste energy. Whenever energy is being wasted, we say that it's being dissipated. That's a key word there that gets used quite a lot. Thank you for the gift. It's dissipated as waste energy. Okay, which material out of these do you think will have the highest specific capacity? What do you guys think of this then? This is a bit of general knowledge, I guess. You got to use a bit of your knowledge here. Highest specific heat capacity. You need to understand what specific heat capacity means. We got the definition already of specific heat capacity. The energy needed to increase or decrease. The energy needed to increase the temperature of 1 kilogram of a substance by 1 degree C. But what does that actually mean? Very simply put, specific heat capacity is how easy it is to heat something up. So how easy it is to raise the temperature, or how easy it is to cool something down. I've got a video on this I posted as well a few weeks ago, which explains this. So out of these things, which one is the most difficult to heat up? So which one has the highest specific heat capacity means which one's the hardest to heat up out of all of these? Usually, yeah. So if it's a good conductor, it means it's easy to heat up. So metals usually have low specific heat capacities because they're easy to heat up. And at the same time, they're easy to cool down as well. That's why when you touch a metal, usually it's quite cold. So the answer is, yeah, well done guys. It's C, it's water. It's more difficult to heat up water. So that's just a bit of a general knowledge. They could ask you that in an exam. It's just to know that if something's a good conductor, it generally has a low specific heat capacity. Well done if you got that. The unit for measuring energy is, this should be straightforward, guys. Give me the answers real quick and tap on the screen a few times. What are the units for energy? This whole topic is on energy. We actually haven't even probably mentioned it. Oh yeah, we have mentioned it when we wrote all the equations, haven't we? Yep, everyone's getting it right. The answer is D, joules. Okay, dreaded 6-mark question here. Looks scary. Let's try and simplify it. What can we take? So we've got a kettle, we've got it in kilowatts. Kilowatts, watts means power. So think of the equations for power. We've got a time here, we've got a mass here, we've got a temperature here. Any idea what equations we need to use here? Here's a big clue for the equations. So power, we're going to need an equation for power. Power, we said, is equal to energy over time, right? Another equation, yes, the specific heat capacity equation. So specific heat capacity, it was energy is equal to mc delta theta, okay? We're going to have to use both of these. So first of all, we're going to use the power equation. The power equation, something's up with it because it's in kilowatts. So we need to first convert that into watts. 2.6 kilowatts into watts, we need to times that by 1,000. That's going to give us 2,600 watts. We can now use that in our equation to work out what energy is. Once we've got the energy, we can then put it into this equation. So energy is equal to, if we rearrange this equation here, energy is equal to power times time. So that's 2,600 times the time. Here's the time, 120. Can anyone tell me what that is first of all? 2,600 times by 120 seconds. That into your calculator and it should you. Yeah, well done. Thank you. 312,000 joules. Okay, so that's half of our calculation done. Kind of. Next, calculate the specific heat capacity. Okay, so what do we have? Do we have everything in this equation? We want to work out what C is. We've been given mass. That's here. We've been given the temperature change. That's here. Energy, we've just calculated, and we want to work out specific heat capacity. So our first job is to rearrange this equation to make specific heat capacity the subject. Thank you for the gifts again, T. So C is equal to energy over mass times change in temperature. So let's sub everything in. We've got 312,000 at the top. At the bottom, we are going to put our mass in, which is over here as 0.8 times by our temperature. Remember, this delta T is our temperature change. So it's our temperature going from 100 to 18 degrees. So what is 100 to 18 degrees? Let's just work out how much that is. 100 minus 18 degrees is 82. Yeah, well done. So 82 degrees. So let's put 82 in there and then just put that all into the calculator and you should get the answer. Let me know if anyone's got it yet. So I'll give you guys a few seconds to try and put that into the calculator and let's see if anyone's got the answer. Yes. Well done. So if you put that all into the calculator, you should get 4756 joules per kilogram per degrees C. Looks like everyone's getting it. And the question, okay, this is 5 marks. What's the last mark for? What do you guys think the last mark's for? It's not for units. Units are given. Significant figures. Yes, give your answer to 2 significant figures. If it ever tells you to give your answers to significant figures, it means that is an extra mark. So make sure you do that at the end. So this to 2 significant figures, 4,800, and that should be our final mark. So let's just compare that to our mark scheme. We did this first. You actually don't even get a mark for converting the 2.6 kilowatts. That's all 1 mark for converting and finding the energy. That's all 1 mark. And then we put it into the equation. We got 82 and then we got 4,756 and our final mark was 4,800. So that was fine. Good job, guys. Okay, I think that's all. Let's do a few more questions and then we'll call it a day. Let me know. When a system changes, such as a roller coaster is going down a hill, energy is created, destroyed, transferred, or static. Hoping this is a quick one as well, guys. The law of conservation of energy. Not static. Energy is never static. Energy, the conservation of energy is never created or destroyed. It is always transferred from one form to another. So the answer is C there. Well done, those of you who got it. Next question. The energy stored in food is an example of which type of energy store? So remember, we learned 8 types of energy store. Here's 4 of them. Which of these is food, do you think? A, B, C, or D? Let me know what you think the answer is and tap on the screen a few times. So we've got some people saying B, we've got some people saying C, most people saying C, it seems. Food is chemical. Chemical is when you release energy through a reaction, some sort of chemical reaction. when you have food in your body and you eat it, there's a chemical reaction going on in your body which releases energy. So it's stored as chemical energy in your food, and then you release it when you digest it. An object being lifted off the ground has energy transferred to which energy store? Okay, hopefully you guys can get this as well. Hopefully this is straightforward. We mentioned this earlier in the live. A, B, C or D. Lifted off the ground. Lifted is the key thing here. What's changing when something's being lifted? Someone asked, what does conservation and dissipation of energy mean? Conservation just means it can't be created or destroyed. Dissipation means it's being wasted, usually as thermal energy. I actually posted a video on this, I think it was earlier this week, talking exactly about this. So I suggest, why don't you watch it after the live? Why don't you just watch that video? It's, I posted it earlier in the week. This one, yeah, it's being lifted. If something's being lifted, its height increases. If its height increases, the only equation that has height in it is gravitational potential energy. So the answer is C. The energy transferred to an object when it's warmed by heater is stored in which energy store? This should be obvious. It's warmed. So the answer is going to be thermal energy. Yes, it is. Good. What happens to the total energy in a closed system? Anyone know what a closed system means? No, it doesn't mean no air. Closed system means nothing, no matter can go in or out of it. So nothing can go in, nothing can come out. And at the same time, no energy can go in and no energy can come out. Basically, our universe is a closed system. We can't add any extra energy into it. We can't take extra energy out of it. And same with matter. All the matter is the same in the universe. So if you have a closed system, nothing can go in or go out. So even energy, total energy, does not go in or go out. So the answer is C. It stays the same. You can't change the energy in a closed system. The energy associated with an object in motion, anything that's moving, would be, let me know what you think. Got a few more questions and then we'll call it a night, guys. Yep, kinetic energy, well done. Answer is kinetic energy. So any moving object, the faster it moves, the higher the kinetic energy. Next one, if a book falls from a shelf to the floor, which type of energy transfer has taken place out of these ones? A book falling, if it's falling, it's starting off at a very high height, yes. And it's moving when it's falling, so that kinetic energy, as it's getting lower and lower, is being converted into let me start again. The gravitational potential energy is getting converted into kinetic energy as it gets lower and lower. That's why it gets faster when it moves down. So, yep, nearly done. When a ball is thrown into the air at the highest point, the ball has maximum, again, hopefully straightforward, at its highest point. This is to do with height. At its highest point, it's going to have maximum. We're getting a mix of answers here. Kinetic, someone said. Thermal, someone said. Gravitational potential, someone said. Not elastic potential. There's no rubber bands or springs involved. Answers not D. Which one is it? When a ball is at the highest point. Highest is the key word here. It tells us it's to do with height. Which one is to do with height? There we go. Now people are getting it. Yes, it's C. Gravitational potential energy. So yeah, guys, I think this is the last question. Check out my other videos on YouTube for all the other topics I've done. I've done a bit of biology. Yesterday we did some chemistry as well. I'm uploading that all on YouTube with all these questions, all the exam questions that we did, the notes that we've written. So all these notes that we've written, I'll give you access to these. So yeah, subscribe to my YouTube channel if you want to see all my future lives and even my past lives. I think I've done about, just in the last month, I've done about 10. So it'll be quite useful for your mock revision. I don't know if you guys have done your mocks or not. Most of you, I know, are doing it over like the next few weeks. But yeah, check it out. How can I get your notes? Yeah, so go onto the videos on my YouTube. Check the comments, not the comments, sorry, what's it called? The description. If you go into the description, I've got links for the notes, for all the questions, and like there's flashcards as well that you can print out. It's basically the questions, but you can print them out as well as flashcards so you can test yourself if you want. It's useful for some people. So, final question. What did you guys say? So most of you are saying C. Energy cannot be created or destroyed yet. That's called the conservation of energy. All right, well done, guys.